Hello, I'm Michael Bunch. I'm the plant pathologist at the North Dakota State University Carrington Research Extension Center. Two of the questions I get very often about white mold management in dry beans are: one, what is the economic return to 1 versus 2 versus 3 fungicide applications targeting white mold in the season? And two, if I'm going to make more than one application, how many days apart should those applications be made? What I'd like to do right now is share with you results from the first year of field studies evaluating these research questions. We conducted this research because white mold management is not very good even at optimal application timings. Disease management or disease control of 50% is considered good with optimal application timing and 2 sequential applications. And applying at that optimal timing is very difficult. As I explain in my companion materials explaining how to optimize fungicide application timing when conditions favor white mold as dry beans enter bloom, there's a penalty to applying the fungicide too early because new growth is not protected, and a penalty to applying the fungicide too late because you cannot eradicate existing infections. Now, on top of the fact that there's a penalty to applying too early and too late, and thus you have a very narrow window for application, it's very hard to target that narrow window because oftentimes our fields are not completely consistent. The dry bean growth stage in one part of the field will be different than another part of the field. And then, of course, not every day is a good spray day. So, what we set out to do in this research is to see whether we could improve fungicide performance either by increasing the number of fungicide applications or by changing the interval between applications. In theory, if we tighten the interval between applications, we can reduce the penalty to applying the fungicide too early because we'll be protecting that new growth that's unprotected. Okay, so we apply our fungicide, we protect the canopy that's there, the dry beans continue growing, and that new growth is unprotected, but then we come back at a tighter interval and protect that new growth, which should, in theory, improve our white mold management. It does, however, create the risk that that second application is going to be put on too early to protect the crop through the end of the bloom period, and we might need a third application. We conducted this testing in Carrington with pinto beans seeded to narrow rows at a seeding rate of 90,000 viable seeds an acre. The spray volume was 15 gallons an acre. All applications were made with a tractor-mounted, PTO-driven sprayer at an application speed of 6.0 miles an hour. We calibrated the fungicide droplet size relative to canopy characteristics. I would recommend that you review the materials I have posted on that subject for more information. All the testing was conducted with a large number of experimental replicates, and this is because white mold disease pressure tends to be spatially inconsistent, and the more replicates that you utilize, i.e. the more times that you randomize the treatments across the footprint of the study, the better your opportunity to even out those differences and increase the odds that every treatment is exposed to areas of high disease pressure and low disease pressure approximately the same number of times. We assessed white mold by individually evaluating every plant for white mold severity in at least half of the plants per plot. And then for harvest, we essentially knifed the beans. The reason why we knifed rather than straight harvested is because the other major variable that can impact our yield data are differences in lodging. And the differences in lodging do not always correspond to differences in disease severity in these studies. If we were to straight cut, we would add a lot of variability into our yield data due to the differences in lodging. We instead essentially knifed the beans. We clipped them at the base, windrowed them, and then passed the clipped beans through the combine once they had dried down. We knifed them because in this way we were able to rigorously assess the impact of the fungicide treatments on yield without any confounding impact of lodging. We applied supplemental irrigation as needed to establish the white mold disease pressure that was required to be able to differentiate the different fungicide treatments. As I mentioned, these were applications made with a tractor-mounted sprayer. In this case, this is a pulse width modulation capable sprayer, and we set the pulse width manually based on the measured spray actually measured spray output. So we mixed the fungicide in the tank, and then right before we sprayed, we collected the output from every nozzle emitted over a 10.0 second period and measured it. If that output was a little bit off, we manually changed our pulse width until the output was perfect so that we emitted precisely 15.0 gallons an acre at our driving speed of 6.0 miles an hour. The applications were made with this tractor-mounted sprayer. This picture was taken in soybeans, but the exact same procedure was utilized in the dry beans. We have a driving pass here that was established actually with a strawberry cultivator. We use that cultivator to smooth out that driving pass so there are no bumps. By eliminating bumps, we make sure that that boom does not sway and that we maintain a consistent 20-inch height between the top of the canopy and the nozzles, as is recommended for the 110-degree nozzles that we utilized. We spray a 10-foot width with no nozzle overlap, and that's the width of our plot. And then what I will show you as I play the video is that there's a stretch between plots for the sprayer operator to turn on and off the sprayer, and that allows him to get the sprayer turned on before he reaches his target plot, and then there's a transition zone again for him to turn off the sprayer after the plot is done. This ensures that the plot is thoroughly and consistently sprayed, that the sprayer operator does not have to stop the tractor between plots, and that there is absolutely no confounding influence of one treatment on another. Okay, so those non-treated transition zones, those transition zones for turning on and off the sprayer are not harvested, they're not assessed for disease. In this case, the treatment plot begins at that blue flag just to the left of the tractor, and it ends at the second blue flag. And now I'll play the video showing this application process. So what did we learn in the study? This slide has bar graphs showing the yield data, and in this yellow kind of light brown shading to the left of the bar graphs, the white mold disease data. That's the percent of the canopy diseased shortly before maturity. You'll notice we tested 5 different application timings. Those timings were consistent whether it was a single fungicide application or the first application in a multi-application sequence. When we tested 2 or 3 applications, we tested those applications at 7, approximately 10, or approximately 12 days apart. Next, I'd like you to look at the non-treated control. You'll see that there is some degree of variability in the non-treated control, with the disease severity of non-treated control varying from about 65 to 75% of the canopy diseased. The yields varied correspondingly, with the average yields in the non-treated control varying from 2,000 pounds an acre to 2,500 pounds an acre. Now, these non-treated controls were located tightly, spatially, with the corresponding fungicide treatments, which means that that non-treated control for a particular fungicide application interval and frequency treatment is a relevant comparison to the application timings within that particular fungicide application frequency and interval treatment. However, you can see that there is variability across those non-treated controls, and what this means is that despite our 9 experimental replicates, we still had sufficient variability in disease pressure out here that these different fungicide application interval and frequency treatments were exposed to different levels of disease pressure on average. And because of that, what's actually most informative in this case is the average yield gain from the fungicide, not the raw yields. Because if the yield was 3,000 pounds an acre in the fungicide treated versus 2,500 in the non-treated control, that's not as good as a 3,000 pound an acre yield in the fungicide treatment versus a 2,000 pound an acre yield in the non-treated control. What matters is the yield gain relative to the non-treated in that particular treatment. Because of that, I have presented the average yield gain conferred by the fungicide. This is the average yield across all 5 fungicide treatments. If you look at that very quickly, you'll notice that there's an enormous difference in the yield gain conferred by the fungicide when you made 2 applications versus 1. Absolutely enormous. And it looks like that yield gain increases as the interval between applications increases with 2 applications. We go from 674 pounds an acre average yield gain across the 5 fungicide timings to 808 as we go from a 7-day interval to approximately 12-day interval. And then if you look at 3 applications, it looks like we can achieve further gains with 3 sequential applications, but only if we get our application interval correct. In this case, we optimized with approximately 10 days apart, 3 different applications. Let's look at these data another way. What I have presented here are the average yields across all 5 fungicide application timings. That's the bar graph in the dark blue. But again, remember, these average yields are compared to a different baseline because the non-treated controls and the corresponding non-treated controls had different levels of disease pressure. So really what matters is the yield gain conferred by the fungicide. That tells you how much benefit the fungicide had, how much benefit that fungicide program had, how profitable that fungicide program had. And that I have presented in the scatter plot on the right. In that scatter plot, you'll see the average yield gain conferred by the fungicide across all 5 fungicide applications. And then with the circles, you'll see the yield gain conferred by the fungicide at each individual application timing. In this case, what we want is a maximum average yield gain and then as little variability as possible across the fungicide application timings, i.e. we want those circles to be relatively tight because we want flexibility on when we spray. So let's look at a single fungicide application. You can see that the average yield gain was just 375 pounds an acre, which was statistically worse than everything else out there. And then if you look at the circles, you see that there's a lot of variability in the yield gain conferred by the fungicide relative to the application timing. So this means that a single fungicide application, first off, did not give us a very good yield gain, and then the fungicide timing mattered a lot. And so that means that a single fungicide application is really something that is going to be suboptimal for white mold management in pinto beans if you have any significant disease pressure. The single application does not give very good disease management, and then second, the application timing matters a ton. You have to get that application timing perfect to get a decent response from that fungicide. Now looking at 2 sequential fungicide applications, what you can see is that we increased our average yield gain from the fungicide as we increased the interval between the applications. And if you look at the circles, you'll see that that the worst performing fungicide treatments were about the same across all of them. When we increased our application interval, what became more and more important was our application timing. And that's what you see with that increased spread with those circles. So essentially, 12 days apart was optimal in terms of our yield gain, but the application timing became more and more important. And so we lost some flexibility in our application timing. But on balance, that was a risk worth taking, because even the worst application timing at 12 days apart was no worse than the worst application timing at 7 days apart. So what these results indicate is that if you're going to make 2 applications, those 2 applications are best made approximately 12 days apart. But what about 3 applications? Now, suddenly the application interval becomes really critical. And if you look at the 3 applications about 10 days apart, we maximize our average yield gain, and then look at how tight those circles are to each other. What that means is that irrespective of the application timing that we utilized, we had very good yield gain from the fungicide. You compare that to 2 applications 12 days apart, and you can see those circles are widely spread out. That means that the yield gain conferred by the fungicide was highly contingent on the application timing. So what these results suggest is that in order to have flexibility in our application timing and to maximize the yield gain from the fungicide, for management of white mold and pinto beans under high disease pressure, we need to make 3 applications approximately 10 days apart. If we don't have the ability to do 3 applications, it doesn't pencil out economically, then we should be doing 2 applications approximately 12 days apart, but then we need to be very, very careful about our application timing and do our very best to make sure that the fungicide is applied at that optimal growth stage for if the conditions favor white mold as those pinto beans are entering bloom. So to reiterate, what these research results suggest is that 3 applications approximately 10 days apart may optimize white mold management in pinto beans. In this research study, we optimized our average yield gain from the fungicide with the 3 applications approximately 10 days apart, but most importantly, we had very consistent results across all application timings, which means that this application strategy gave us the greatest flexibility in our application timing. We could go on a bit early and still get good white mold management. If you cannot afford to do 3 sequential applications, then, and you can only do 2 applications, then these research results suggest that approximately 12 days apart between applications is optimal. However, then the application timing becomes critical. Now, let me stress that these are preliminary results from the first year of testing. We conducted the testing very rigorously, but we need to have results over multiple environments, either multiple years in Carrington or multiple study locations or both, before we can have full confidence in these recommendations. We are doing follow-up testing in 2025. The other thing I would mention is that in this testing, we applied Endura at 8 ounces in every single application. We did this purely for logistical reasons. It allowed us to mix up the sprayer and apply all of the plots that needed spraying on a particular day with a single load, and allow us to drive over the study just once in every application. I would recommend, when making more than 1 application, that you rotate your fungicides. We typically see better disease management that way, and also it's better for fungicide resistance management. But for logistical reasons, and only for logistical reasons, we applied Endura in every application in this study. Before I close, I would give very sincere thanks to my staff, Aaron Faust, Swan Collis, Jesse Hafner, Gabby Henson, and our student workers. It's the highly dedicated efforts of these individuals that has allowed this research to be conducted. Sincere thanks to the funding agencies that provided the support financially for this research. The North Harvest Bean Growers Association, these are your checkoff dollars, and the North Dakota Crop Protection Product Harmonization and Registration Board, administered by the North Dakota Department of Agriculture. These 2 grant agencies provided the funds to pay for the salaries of my staff, and also provided the funds to pay for all the costs of the supplies and repairs associated with conducting this research. I'd also like to give sincere thanks to the private companies that do contract testing with us, because it is the funding associated with that contract testing that allows us to invest in the equipment needed to conduct this research. That tractor and that sprayer that you saw in the video, that was purchased with funds from that contract testing. Our combine was purchased with funds from that contract testing. This contract testing is essential to our operation, and we are grateful for the companies working with us to do that. Finally, I would give my very sincere thanks to Bollingberg Seeds Company and Green Valley Bean Company. These two companies donated the seed for this fungicide application interval and frequency testing work in pinto beans and in kidney beans. Thank you for your time, and I hope this information is of use to your operations.